you, Fabián, for that introduction. Again, I want to thank you all for coming. I appreciate your support. I have really enjoyed this project, so I'm also very excited to present all of the results and findings that we found. And if at any time any technical difficulties arise, I'll just stop my video and try to do it without video, just in case my bandwidth isn't big enough, but it should work. So as Fabián said, my name is Jessica Wayment, and my project was on nitrate leaching mitigation using Kura Clover and winter rye in corn and soybean systems in irrigated sandy soil. And to start off with, an outline of my study. So I'll start with the background of the study, a little bit of why we decided to start the study and why we're continuing it, and then move on to materials and methods. And then my results and discussion are divided into two parts. The part one is more of an agronomic side, looking at Kura Clover rye's and nitrogen's influence on the corn and soybean systems. And then part two is more of the water quality aspect, looking at the nitrate leaching reduction from the Kura Clover and rye. And then I'll end with conclusions and then with acknowledgements at the end. So nitrogen is the most limiting nutrient in non-leguminous crops. And because there's little toxicity concern in corn with over-application, it's commonly over-applied to ensure crop yield. And nitrogen in the form of nitrate is easily leached through the soil. And agriculture sources of nitrate contamination are a major source. While sandy soils represent a small fraction of agriculture land in Minnesota, they are also highly productive. And in order to increase this productivity, due to the low water holding capacity, they're commonly irrigated. And many times they're referred to as leaky fields because they're very vulnerable to nitrate leaching due to this low water holding capacity and typically high precipitation events. And so, as I just mentioned, the combination of nitrogen inputs in these coarse textured soils, as well as irrigation, this is a formula for a highly productive agriculture system, but it's also a formula for a highly susceptible system for leaching. And not only is nitrate leaching a monetary loss for growers, but it's also extremely costly to remediate contaminated drinking water sources from nitrates. And elevated nitrate levels above the US EPA's drinking water standard can pose a health threat to humans. And additionally, the loss of nitrogen, especially nitrate, into surface water is also a threat to aquatic life. And recently, sandy soils have been the focus of increased regulations on nitrogen applications. And in more recent years, restrictions on fall nitrogen applications have been implemented. So to further reduce the nitrogen application restrictions, as well as environmental and human health concerns, management techniques besides best nitrogen management strategies need to be implemented to further reduce the potential for nitrate leaching from these sandy soils. One of those strategies is to integrate cover crops. And not only have they been shown to reduce nitrate leaching, but they also help reduce erosion and fertilizer inputs and can increase soil health by adding organic matter. They've also been shown to suppress weeds as well as increase crop yields. So two of the cover crops that we used in our study was rye and Kura Clover. We chose rye because it's an annual cold season grass, and it's helpful to prevent leaching during the off season of the crop, so fall and early spring, when leaching potential is very high. And Kura is intercropped as a living mulch and is helpful to prevent leaching all year long as a perennial cold hardy legume. Its rhizomatous root system helps it to become established and be persistent. And this persistence also does require suppression to reduce intercrop competition. So now I will go through my materials and methods section. And starting with our study site, this, as Fabián mentioned, it began in 2011, and this aspect of the study began in 2016 as part of Natalie Rick's master's research. And so her data from 2016 to 2017 is combined with my data from 2018 to 2020. So the study was located in Westport, Minnesota, on an Arvia sandy loam with 4.6% organic matter, which is relatively high for sandy soil. And the mean precipitation was 635 millimeters, and a mean annual temperature was 5.8 degrees Celsius. Irrigation was applied with the linear move system, and scheduling was done based on the checkbook method. And the soil moisture was also monitored to ensure that the checkbook method wasn't over-applying or under-applying the irrigation. And typically we had 7 irrigation events per season. And in 2018, due to adequate moisture throughout the season, we only had to apply it twice during the season. So the site was established in 2011 with these 3 cropping systems, denoted as corn, soybean, soybean-corn, and corn following corn, or continuous corn. And just as a side note, for the analyses that I will present later, I use CSB to denote all of the corn grown in the rotation, and SBC to denote all of the soybean grown in the rotation, and then CC for continuous corn. The study was set up in a randomized complete block design with 4 replications and 12 treatments, and I'll talk about these 12 treatments in just a little bit. We installed moisture sensors in various plots to record moisture and temperature, as well as 216 ceramic cup suction tube lysimeters installed with 3 per plot in 10 of the 12 treatments. We also have 5 passive lysimeter drain gauges in various treatments as well to measure drainage. Nitrogen was applied at 5 rates in no cover and rye plots, and Kura Clover only had 2 rates, 0 and then 200 in corn soybean and 250 in continuous corn. For crop management, our plots were strip tilled throughout the study, and rye was seeded at crop R6 stage and then chemically terminated prior to planting. And in 2016, Kura was drill seeded with an oat companion crop, and then it was terminated after it was 10 centimeters tall. And then after the establishment year, we intercropped it in 2017 with with corn or soybean, depending on the rotation. And in the spring, we also applied glyphosate at a half rate to suppress the Kura in the interrow. And then in 2020, we decided that we needed to increase the suppression. And so we applied herbicide at the half rates in the interrow and at full rates banded within the row, just to really knock back the Kura. And then urea was incorporated after being applied in split applications. It was incorporated after a few days, either by rain or irrigation events, to reduce volatilization. And then to further reduce volatilization, we applied a urease inhibitor to also minimize that effect. Plant tissue samples were collected at V8, R1, and R6 for the corn, and just at R6 for soybean. And then they were analyzed for total nitrogen, as well as for harvest grain and the cover crop biomass at pre-planting and then post-harvest. And soil samples were collected at V8 and R1 and post-harvest and analyzed for nitrate and ammonia. Weekly water samples were collected from the lysimeters and analyzed weekly for nitrate. Our soil moisture probes were set at hourly recording intervals for moisture and temperature. So moving on to my calculations, the water balance method was used to calculate drainage, where the soil water content plus precipitation plus irrigation minus our evapotranspiration, or ET. And our ET was calculated based on the Penman-Monteith method and adjusted with the FAO 56 method, where we used a KC value or crop coefficient that was adjusted for the Minnesota climate. And for Kura, we used a KC value for alfalfa, since there has not yet been a KC value for Kura established. And then a crop stress coefficient, or KS, was additionally applied for the adjustment of when we applied less than optimum nitrogen, or when yields were impacted by one of the covers, specifically with Kura. And drainage, as I mentioned earlier with the drain gauges, was also measured by these lysimeters just to give a general value of drainage, as they weren't in every treatment. And so this was used to double check the values with the water balance equation that I did. And nitrate load was calculated by drainage multiplied with the concentration. And per standard procedure to present leaching results, we also calculated the flow-weighted nitrate concentration. However, because our drainage was so individually calculated based on the treatments, the results were similar to our load results. And so today, I will just be presenting the load results. We also did a partial nitrogen budget that was very simplified. And our inputs included were fertilizer and then biological nitrogen fixation from the soybean. And then our nitrogen outputs were from plant nitrogen uptake, grain removal, and then from nitrate leaching. And then we included the change in soil total inorganic nitrogen using the residual soil tin from the end of our study minus the initial soil tin from the beginning of the study. Statistical analysis was performed using the R software, using the linear mix model procedure in the LME4 package. And we were looking at the interaction between cover and nitrogen rate with replication as our random factor. Alpha value of 0.05 was used in the ANOVA significance. And then mean separation was further used to explore the differences between treatments. Our EONR was determined from a quadratic plateau regression model using the corn to nitrogen price ratio of 0.01. So now we get to go to the good stuff. Part 1, results and discussion. And this is, again, like I said, the agronomic aspect. So the objectives of this study, aspect of the study, were to determine the impact of rye and Kura on soil nitrogen availability, corn and soybean nitrogen uptake, and corn and soybean grain yield at these variable nitrogen rates. So to begin with cover crops, here's a table with rye and Kura's biomass, and then below is their uptake for each of the cropping systems and for each of the 5 years. And we also noticed that nitrogen rate did not affect the covers. So the values in this table are average between all of the nitrogen rates. And some common trends that we noticed was that over all the years, once it was established, Kura remained relatively constant as far as biomass and uptake, regardless of the year or cropping system, really. Rye, however, showed a positive response between growing degree days in each year and the biomass. And we also noticed with temperature that fall temperatures were below average almost every year of the study. And we also noticed that in corn-soybean, the rye biomass was the greatest. And so not just temperatures, but corn residue can affect rye establishment. And it does better when it's seeded into soybean residue. Then we also found no significant differences in total organic carbon or inorganic carbon between the cover types. So moving on to corn nitrogen uptake from the plant samplings. Averaged across 2017 to 2020, this graph is showing the different stages of corn sampling at V8, R1, and R6 for both corn-corn and corn-soybean, for rye, no cover, and rye. And the blue line for rye and black line for no cover and green line for Kura will be consistent throughout this presentation in each of my figures, just to help you follow along. And rye was similar to no cover in each year, except at R6 when it was greater. And this may indicate that the rye after termination becomes mineralized, but it becomes available later in the season, which allows more nitrogen to be taken up by the corn in the rye treatments later in the season. And Kura reduced corn nitrogen uptake by 23% on average. except as I mentioned earlier, in 2020, when we applied greater suppression to the Kura, corn nitrogen uptake was actually similar between Kura and no cover. So now soybean nitrogen uptake, although there was no statistical difference between rye and no cover, there was still a 4% reduction in soybean nitrogen uptake. And Kura, although it was not significant each year, it on average reduced soybean uptake by 18%, which also is corresponded to what we saw with yield. So this table is averaged from 2017 to 2020. And Kura reduced corn by 36% in corn and by soybean yield by 20%. And an interesting trend that we found in 2017 and 2019 years, corn grain from Kura was reduced by 36%, and then by 15% in years 18 and 2020. And the differences in these yield reductions may be attributed to the cooler and wetter springs, which were seen in 2017 and 2019, which may have favored Kura growth and increased the competition. And as we see in continuous corn, there was no difference between Kura and no cover with yield as well. And this is due to that more aggressive suppression that we performed on the Kura to really help the corn get ahead earlier in the season. And rye also significantly reduced soybean yield, but not as badly as Kura did, and it was only by 0.2 micrograms per hectare on average. And comparing rye and no cover yields at each of the nitrogen rates and the 3 cropping systems, both rye and no cover showed positive corn yield response to the nitrogen applications. And at the higher nitrogen rates, rye did not significantly increase yield compared to no cover. And I'll talk about why this is important in just a few slides as we go on. So moving on to EONR, this graph is showing the nitrogen rate here on the x-axis with yield in megagrams per hectare on the y-axis. And this is the quadratic plateau regression line between rye and no cover. And as you can see, especially in continuous corn, it's very similar. And then the black dot represents the EONR with no cover and the EONR in rye with yield. And same for corn soybean. And this is for 2016. And this is over all 5 years. And although it's not consistent every year, in 3 of the 5 years, both continuous corn and in corn soybean, rye minimally increased the EONR without increasing the yield. And now I'll come back to the EONR graph after talking about the soil sampling. So this figure shows soil total inorganic nitrogen at each of the 3 sampling periods, V8, R1, and post-harvest, in each of the 3 cropping systems for rye, Kura, and no cover. And rye was similar to no cover most of the years, but Kura had higher total inorganic nitrogen at V8 and R1. And as we saw previously with the corn nitrogen uptake, there was a lot of competition. And so although the soil total inorganic nitrogen was higher with the Kura, this wasn't available to the crop during those times, indicating that Kura just outcompetes the crop for nitrogen. And the V-shaped trend also shows how at the beginning of the season, when we apply fertilizer, there's more nitrogen available, and then it drops down at R1, indicating active crop nitrogen uptake. And then we see it increase again as some of that residue begins and nitrogen begins to mineralize and increases as crop nitrogen uptake decreases. And this also helps indicate that nitrogen leaching potential is greatest earlier in the season and later in the fall. So continuing with soil sampling, this graph is starting to tie in more of what we talked about with EONR. So on the x-axis, we have the change from EONR. And so 0 represents the EONR with the red dashed line. And then all of the negative values is anything applied below the EONR. And then the positive values are nitrogen applied above the EONR. And then each of these dots represent the EONR for each of the individual years based on rye or no cover, with residual total inorganic nitrogen on the y-axis. And as you can see, so from starting from less than 100 kilograms of nitrogen below the EONR up until over 200 kilograms above the EONR, residual nitrogen from rye was greater than in no cover. And the fact that when nitrogen below the EONR is applied in the rye, the residual total inorganic nitrogen still increases, indicates that this is not as much a nitrogen management correction as it is a management of rye, which I will talk about in the next slide as well. So going back to the EONR figure and now incorporating residual total inorganic nitrogen on the right y-axis, you can see as rye minimally increased the EONR without increasing yield. And you also saw that above the EONR rate and at the EONR rate, rye increases residual nitrogen. And while the fate of nitrogen is really unknown due to the limitations of this study, what most likely occurred was asynchrony between the terminated rye biomass mineralizing, but being available to the crop after nitrogen demand peaked for the crops. And that's why the residual nitrogen is greater and would be susceptible to nitrate leaching. Some other studies have shown that rye can also increase immobilization or volatilization, which may have led to this increased EONR. And so now we're going to move to the next section, or part 2 of the water quality aspect. And this the objective for this part of the study was to determine the ability of rye and Kura to reduce nitrate leaching. And so we'll begin with soil moisture. And these figures show the volumetric water content throughout the growing season compared to each of the 3 cover types from 2017 to 2020. We did have soil moisture probes in 2016, but they weren't in every treatment. And so that's why just these 4 years are being presented. And we noticed pretty similar trends each year, but especially between 2017 and 2018, and then between 2019 and 2020. And these bars show precipitation and irrigation events in millimeters on the right y-axis. And we also noticed that a trend with the Kura was lower soil moisture at the beginning of the season, and then typically greater soil moisture with the Kura and the rye at the end of the season. And the early season deficit of moisture from the Kura may have led to some of this early season competition with the cash crops. And then the available moisture at the end of the season from the rye and Kura is most likely due to the soil being covered and reducing evaporation compared to no cover. So now we'll go to drainage, and this is a big table, but I'll break it down. So drainage was compared between the cropping systems and cover, and then each year. And then we divided it based on the nitrogen variable. So when nitrogen was applied below optimum levels, we included it in our calculations as nitrogen limited. And then when nitrogen was applied at optimum and above, that was non-limiting. So that's what those 2 values are. And then comparing my calculations with the drain gauge calculations, they were all within 46 millimeters of the drain gauge values, which helped assure us that our drainage was in the ballpark of what we were seeing in the field. And average drainage from the nitrogen limited were 51% of the total water inputs. And in the nitrogen non-limited, they were 42% of the total water inputs. And this is most likely due to the stunted nitrogen deficient treatments in the corn, allowing more drainage to occur because less water was being taken up. And decreasing the nitrogen rates below optimum can have these detrimental effects because increased drainage can increase the leaching potential. And then soybean drainage was also similar to the nitrogen limited corn crops because the biomass is just not as much in soybean as it is to corn and doesn't take up as much water. meaning that leaching can also be higher in soybean corn based on the amount of drainage that occurs. So overall, Kura reduced drainage by 39% of water being applied. So water inputs include precipitation and irrigation, while Rye reduced drainage by 49%, and then no cover reduced it by 52%. And so as we can see that both Kura and Rye are adequate in reducing water being drained from the soil compared to not having any cover at all. And so now we'll move to concentrations. And this graph is showing the concentrations between the cover types and the years for each of the growing seasons and for the 3 covers. And just a thing to note, in 2016, you can see the Kura has pretty high concentrations in each of the cropping systems. And this is most likely due to nitrogen being applied in these plots to aid in establishment without having a cash crop to uptake it, which may have led to these increased concentration values. Additionally, in continuous corn, Kura concentrations were reduced by Kura by 50% after it was established, so from 2017 to 2020. And in corn-soybean and soybean-corn, Kura reduced it even more by 64%. And this graph is showing the differences between concentrations from the cover types and the nitrogen rates. And averaged across each of the cropping systems, we noticed that it was actually similar concentrations, about 18 milligrams per liter. And in the check plots of corn-soybean, you had 6.3 milligrams per liter greater than in continuous corn. And although both of them didn't receive any nitrogen, and even in the soybean corn, this is most likely due to less immobilization and more mineralization of the soybean residue in the corn-soybean system, which may indicate that, again, managing these, not just the nitrogen inputs, but also these annual cropping systems is important to reduce leaching. And we also noticed that in each of the cropping systems, even in soybean corn, where no nitrogen is applied for that season, it's just residual, they all follow a trend of increasing with nitrogen rate. Although in corn soybean, it wasn't significant, and it's just a very slight increase. So now we'll move on to load, which is including the concentration and drainage, as we saw with my calculations. So first I wanted to show the first year of Kura in 2016, because it didn't follow the same trends after it was established, as we saw with concentrations. However, the concentrations were still lower than no cover in corn soybean, where it had 53% higher load than rye and no cover. Rye and Kura Clover, sorry. And one of the things, and we were kind of wondering why this happened, and I looked back at the concentrations, and Kura and no cover actually had similar concentrations this year. However, because Kura reduced drainage so much, the load was lower in the Kura. And so this can indicate that although drainage is a heavy driver of load, and by having a cover crop that can act as a good buffer, leaching can actually be mitigated. And so now we'll move on to load from 2017 to 2020. And again, this figure is showing load between each cropping system and cover type in each of the 4 years after Kura was established. And overall, in continuous corn and soybean corn, rye was similar to no cover each year. But in corn soybean, rye reduced load by 31%. And again, as we talked about with the biomass being the greatest in the corn soybean, rye had the greatest stands in that system, and therefore was able to reduce leaching significantly. And Kura reduced load by 52 to 75% at the no nitrogen rates, and near optimum nitrogen rates, Kura reduced load by 13% in corn, by 71% in soybean corn and by 31% in soybean corn. And this is just a side note, an interesting perspective. No statistics were done on these differences, but we just wanted to look at how cropping system influenced leaching, because as we noticed with concentrations, they were similar between each of the cropping systems. So averaged across each of them, they were all around 50 to 55 kilograms per hectare. And this graph is showing how during a 2-year season, which incorporates 2 years of corn and then corn-soybean rotation with both phases of the rotation, and how much nitrogen is applied during that 2-year phase. And this is based on the data from 2017 to 2020 that we saw. So even though in corn you apply double the amount of nitrogen that you do in corn and soybean, and much more than in soybean corn because it's just the residual nitrogen, you have pretty similar loads between each of them. And even at the highest nitrogen rate for corn soybean, you have even more leaching than in continuous corn. And some things that may affect this is that the ET in corn is greater than soybean, as we saw with drainage. And so nitrate leaching potential is greater in soybean compared to corn. And although we didn't measure immobilization and mineralization, it's possible that immobilization is higher in continuous corn due to the heavy corn residue, and then mineralization is higher in soybean rotation, which then leads to this higher leaching value. And this also indicates that nitrogen applications are not the main culprit in these leaching issues, but it's actually an annual cropping system management thing that requires further and precise techniques to avoid leaching. So now I'm going to explain how our load was distributed throughout the growing season. And this graph has a lot going on, but again, I'll walk through it. So it's showing throughout the season, the load, and the bar graphs are showing precipitation in gray and irrigation in the yellow in millimeters. And then each of the lines represent the cumulative load for rye and no cover and Kura at the different nitrogen rates. And this is just for 2017. Instead of showing all the graphs which followed similar trends, I chose just to display this one. And the dashed lines represent the different timings of the split fertilization events. And overall, half of the load occurred during the months from May to June, and then tapered off throughout the year. And part of the reason why load was a little bit greater than in the fall is because of some extreme precipitation events that we saw in 3 of the years of the 5 years of this study, where in just one irrigation event, over 80 millimeters fell multiple times throughout the season. And during these times, we were looking at the load during that week. And in Kura Clover, drainage was much lower and load was much lower in Kura compared to the other cropping systems, which is especially important as climate models have predicted more of these extreme precipitation events to occur in the future. That if you have a cover crop that acts as a good buffer for these extreme watering events, you can reduce drainage and consequently leaching. And so now we'll finish with my nitrogen budget. And this table has a lot, but before you get lost into it, you mostly just need to focus on these gray lines, which are the nitrogen balance. And the positive values mean nitrogen was gained into the system, and the negative values is when nitrogen was lost. And at the no nitrogen rate, Kura has a smaller deficit compared to rye and no cover. And at the higher nitrogen rate, Kura has a much greater balance compared to rye and no cover in each of the cropping systems. And then again, a smaller deficit in soybean corn, meaning that Kura supplies this system with nitrogen, not in the form of biological nitrogen fixation, but because it reduces grain yields and reduces load, allowing more nitrogen to be present in the system. But again, the scope of this study didn't measure immobilization and other pathways of like gas emissions, but there could be potential for more nitrogen loss from these systems because there's just all this excess nitrogen not being taken up by the crop or leached. And then rye, similarly to Kura in corn-soybean at the higher nitrogen rate and the other rates also increases the nitrogen balance, which means, again, more potential for nitrogen loss through other pathways of the cycle. And so now I'll move on to my conclusions. And this study showed that leaching was strongly correlated with irrigation and precipitation events. And having cover crops that can buffer these events, such as Kura Clover especially, may become increasingly important. And higher applications above the EONR increase, so when nitrogen is applied below the EONR, you have increases in drainage and potential leaching, which shows how important it is to apply nitrogen at optimum rates, especially because on the flip side, nitrogen above optimum, so in excess, is really a lose-lose situation because you don't have a yield increase and you have even more leaching occurring. And as I mentioned with the 2-year difference in how much nitrogen is applied to a corn-corn crop versus a corn-soybean rotation, it's also important to manage our annual cropping systems as much as our nitrogen management. And in order to really see the benefits of our cover crops, you need to synchronize the cover crop termination and then mineralization with the cash crop nitrogen uptake. And again, understanding the full nitrogen balance and when the mineralized biomass will become available is vital to really understand these cover cropping systems. And during the establishment phase of Kura, because it requires a fallow period, it may be difficult to widely accept this Kura into commercial growers' fields as a stumbling block. But however, once it's established, it's very persistent. And again, this persistence is good because it reduces drainage and nitrate leaching, but it also requires a lot of suppression early in the season to avoid competition with your cash crop. And as we mentioned before, it's a great buffer to reduce the loss during these extreme precipitation events. And because rye doesn't negatively impact corn yield and requires no fallow period, it may be more readily integrated into commercial growers' fields because it has less risk. However, environmentally, there are still some concerns that need to be managed in order to avoid, such as increasing residual nitrogen and in soybean corn, the yield reduction and leaching increases. And since we saw leaching reductions in corn-soybean, it may be best implemented during the corn phase of a soybean-corn rotation to really reap all the benefits that it has to offer. And again, synchronizing the termination of the rye biomass with corn nitrogen uptake and demand is vital to avoid all of these negative potential impacts that it can have. And again, challenges with establishment in corn residue may be addressed by drilling the seed in to the residue to really establish good seed to soil contact can help with establishment. And overall, cover crops show great potential to reduce nitrate leaching from corn and soybean systems in irrigated sands. However, precise management is necessary to reap all of the agronomic and environmental benefits that they have to offer. And to end, I would like to acknowledge all of my committee members, Fabián, Vasu, and John for being on my committee, as well as Natalie Ricks for all of her work for the 2016 and 2017 work, and then the SWAC field crew and the student helpers and all of the land and atmospheric science faculty and graduate students, as well as the Pope County Soil and Water Conservation District and the Minnesota Department of Agriculture for providing funding through the Clean Water Fund and Land and Legacy Amendment. And I will, open it up to questions.
All right, well, very good, Jessica. Thank you for your seminar presentation. Let's give her a virtual round of applause. If you have the little reactions, you can do that. And as Jessica mentioned, we will open it up now for questions and answers. So if anybody has a question, you can open your mic and ask the question, or you can type it in the chat box and I can read it.
Hi, Jessica. This is David Mulla. I really enjoyed your presentation. You did a lot of great work.
Thank you.
I have one question to start with. How much nitrate leaching did you get from the rye during the time that it was actually growing versus how much nitrate loss did you get from the crops during the time they were actually growing?
Yeah, during the early spring, we didn't notice that much difference. And because when we were measuring leaching, so we started measuring the leaching pretty early in the season, but we didn't have all of the data. So like soil moisture and different things. But judging off of the values that we did get, there was more leaching reductions later in the season compared to earlier in the season from the rye. And so it's most likely due to the greater, and although it wasn't statistically different, it was still greater biomass in the cash crop from the rye being mineralized and then available to the crop. Did that answer your question?
Thank you.
Fabián, I got a question for Jessica. Jessica, very good job. I got to read your thesis to understand a lot of material that you covered. I got a just clarification and then a question. In one of the diagrams, you mentioned 500 and 600 kilograms of nitrogen per hectare in continuous corn. Did you apply that amount of nitrogen?
No, so that was that chart. I can go back to maybe. So it was just showing on a 2-year average. Oh, here it is. Sorry, it's not catching up with me. So on a 2-year average, we wanted to show, sorry, not a 2-year average, on a 2-year span, we applied that much nitrogen to a continuous corn system. And then over 2 years for a corn-soybean system, we applied less than that. So we only applied nitrogen during the corn phase. So does that help to clarify?
Yeah, right here. Yeah, so not really. So are you saying this is over 2-year period on the left-hand side, that graph?
Yes.
Okay, it's over 2-year period.
Over a 2-year period, yes.
Okay, all right. That and then you mentioned N-limiting, where you had N-limiting treatment, you had less drainage than the, non-limiting or something?
Yeah, so in nitrogen limited, when nitrogen was applied in deficient levels or below optimum, we had more drainage.
And then you mentioned it's something to do with the evapotranspiration. And but in your calculations, you had already used a coefficient called Ks, which is a crop stress coefficient. So that means it could be wrong the way you are calculating the crop stress coefficient.
So the nitrogen limited are based on that coefficient. So I calculated them differently. So when there was nitrogen limited, or so the nitrogen was deficient, then I used the crop stress coefficient. But when it wasn't, I didn't use it. So does that make sense? So they're calculated individually based on their ET, on the actual ET values. So that's why drainage was more, because the ET values were smaller in nitrogen limited.
So, I mean, if the ET is small and it's limited, that means maybe you didn't use the right crop stress coefficient. It should have been more or less. I thought the crop coefficient takes care of the problem that you're trying to evaluate.
Oh, okay, I see. So we were, I guess, adjusting it based on that value, if that makes sense. So we weren't really using the crop stress coefficient to adjust for anything. We were trying to calculate it based on whatever stress it would have had. Maybe I don't understand your question exactly.
That's okay. Good job. I'll read your thesis. I think I'll
Okay.
understand it.
Okay.
Thank you.
I actually have
questions?
another question on the drainage also. We've been doing some modeling on the data from the Rosholt farm. And so our modeling doesn't use the same method you have for estimating drainage. We're using, some physics-based algorithms that actually calculate infiltration. And we use an energy balance like you did for the evapotranspiration. But our numbers for drainage are a little bit lower than what you're coming up with. So I'm just wondering, what's the and your drain gauge seems to be quite a bit higher for like 2017 than it is in other years because of the wetter climate, but still those numbers are about 100 millimeters higher than what we're getting for the same year with more of our process-based modeling. So I guess I'm wondering what levels of uncertainty do you have in some of the components here of your water balance?
Yeah. When we were calculating drainage, we compared values with other people who have had studies there too, and mine were pretty high compared to theirs. Theirs weren't in my same section, and some of the things that we were using to record drainage, and we also did notice that our drain gauge values were also quite a bit higher than the other people's values that they were measuring. And so part of it could come from our soil moisture sensors, which we were using also to calculate the soil water content. They were a little bit higher than other studies. However, I also found other papers that in sandy soils, they found similar drainage values to ours. And so we decided to go ahead and accept them.
And just to follow up a little bit with that, David, this has been certainly one of the areas where we or Jessica spend the most time trying to figure out how to best do the drainage estimates, because obviously this impacts the load substantially, and it is a challenging part of the study.
And if I can just add one more thing, although the drainage values were greater than maybe what you would typically see, it's also just looking at the differences between the cover types that I think is a little bit more important to how Kura was lower than the other covers. And Rye also was lower than no cover.
Can I ask a question?
Yes, go ahead.
Hi, Jessica. Thanks for that talk. Can you go to you had a slide where you put together a nitrogen budget, and I was a little, I don't know, surprised or confused. thought I heard you say that the biological nitrogen fixation doesn't it's not important with the Kura, or it doesn't influence these results. Can you talk a little bit more about that?
Yeah. Sorry, I didn't have a lot of time to go through each aspect, so I appreciate you bringing that up. We looked at the Kura this year to look to see what type of nodulation it had, and we found that the Kura had no nodulation. And so in the past years, it hasn't been fixing nitrogen. And so we went back and redid these calculations without including the BNF for Kura.
Oh, that's really interesting. So it was essentially functioning as like a permanent cover crop, but it wasn't providing any kind of nutrient benefit to the cash crops. Okay, thanks.
We have time for maybe one more question. All right, well, Satish, you have a question?
Yeah, that's more for you and other people who are going to be pursuing this study later on. I think it seems like estimating drainage is one of the biggest problems, because if Jessica's number 50 kilogram per hectare is a nitrogen loss, that's a lot of loss. And that may be mainly because we have a difficulty measuring the drainage. So I was wondering if, and that's Jessica's conclusion too, that having drainage, maybe managing water might be more important than nitrogen applications. And so what are you guys thinking of doing? Taking a little sample in a sandy soil is very difficult. And some of our ET values, you can use sophisticated models and they're no good either. And then we use crop coefficients and we don't have a good handle on those from year to year. So where are we going? Maybe Jessica can guide us where to go, or you can answer that, Fabián. Thank you.
Jessica, do you want to take a stab at that, and then I can maybe add some?
Yeah. So when I first started looking at drainage and figuring out how we were going to calculate it, because I had 5 past historical years, basically, that I had to kind of catch up with drainage. I thought of some methods in the previous, in the future studies to be able to do and to measure ET directly in the field. It takes a lot of work, and it's very time consuming. And so, but that's one of the potential options to really actively measure it real time.
Thanks,
But, you know, one of the other things too, I mean, as you mentioned, Satish, this is obviously drainage, understanding the drainage and calculating it correctly is the biggest challenge with these kinds of studies. But like you pointed out, I think water management is so important. We see it here with irrigation and precipitation. That is those large rain events where we see the most loss. And sometimes even with the split applications, and you know, we are, as I mentioned at the beginning of the seminar, this has been kind of a hypothesis driven process where we learn things and then we start a new study trying to get to the next level of questions. And so we have improved quite a bit in terms of, okay, we know what best management practices are for nitrogen. We are splitting the application. We are trying to apply most of the nitrogen later in the season. And still we see that whenever rain comes and in excess, that's where we have the biggest potential for loss. And the challenge in these particular soils is that they are very shallow. I mean, they don't have a lot of, to begin with, they're sandy soils, so they don't have a lot of storage capacity. And then the other part is that the profile is very shallow. You know, 1.5 foot depth is kind of the average. And after that is gravel, and so it's pretty hard to retain any of that excess water. And so trying to find a way to sequester nitrogen through cover crops that will then release in time for the cash crop to use it, I think is that kind of the center of what we need to be looking at. because, and then obviously irrigation, managing irrigation correctly is important because then we have the challenge of precipitation that we have no control over. I am actually excited to see the numbers for this year, how the data is coming this year, where we actually were able to manage water a lot better because basically we were dependent on irrigation with a lack of precipitation. So I don't know if I answered completely your question, but it's certainly something that is a big challenge. And then the other part too with ET values, for instance, in these intercrop systems where you have Kura and rye and corn and soybean, trying to come up with a value that is adequate. There are not really a lot of studies where people have looked at this intercropping with Kura, and so we kind of resorted to, for instance, using alfalfa as a surrogate for the Kura plots. So there is still a lot of work to be done.
Thanks, you guys. I think the main point I'm trying to make is, and for several years, that we have been spending a lot of time looking at concentrations and doing this and that, where the biggest unknown that we have or a handle on it is the drainage. And we come up with, really high numbers or very low numbers, and it gives a wrong impression that that's what the number is. But I think for the experiment, you're looking at relative values, which is okay. But people, if they think we are losing 50 pounds or 55 pounds, that's a lot of nitrogen going in there. So anyway, thank you for answering my question.
And thank you, and thanks for the questions. Thanks everybody for being here today. And I would now invite you to do another round of applause, virtual applause, and then if you could log off the meeting, because we'll move on to the defense portion of the seminar. Thank you.